All right, as it says, oh, by the way, one mistake of many that you're going to have to change, that is no longer Chapter 20. We have a new book now. So Chapter 19. And then there's a couple of references to the old book in here, and I'll let you know when those come. Okay, so as it says, the title is Electrochemistry. All that redox stuff that we were talking about, that was getting you ready for this. Okay? Here's just some, basically this is a skills kind of thing. You're going to become, hopefully, familiar with the structure and or the components of electrochemical cells, which they can either be, there's two names, either galvanic or voltaic. Either of those names are used interchangeably. You use them as the word battery. Okay? But those are either galvanic or voltaic cells, meaning that it's the same thing, or an electrolytic cell. Okay? We'll talk about the difference on those. And within those types of different cells, we're going to have to differentiate between whether it's a voltaic or electrolytic cell. And all that refers to is which direction is the energy flowing, and is it going to be a spontaneous or a non-spontaneous process depending on which direction we're referring to. We're going to learn to calculate cell EMF, which you guys call voltage. Not at this time. This is going to be the fourth quarter, like a week or two before we start reviewing for the exam. We'll come back and pick up like the last two sections of Chapter 19. In order to do the part there where it says determining the spontaneity quantitatively and using that Nernst equation, we need to know about equilibrium. You guys don't know about equilibrium yet or how to calculate things with equilibrium yet. So when we learn that, then we'll come back and throw these in. And then we're also going to look at looking at some electrolysis calculations. All right, so here we go. And again, these two words are used interchangeably, a galvanic or voltaic cell. What are the components? Well, I drew a nice little picture there at the bottom, which I stole from somewhere. I can't remember where that came from. We'll talk about what all those little pieces and parts are here in a little bit. But anyway, one of them is going to be the anode. I'm actually going to write some information up here. The anode is, and you should have some bullet points there, right? Okay, the anode is where oxidation occurs. Or if you're talking about a redox reaction, it's the oxidation half reaction. So oxidation takes place in the anode, and that process is what the oxidation half reaction would be. This is the source of electrons. So in a battery or galvanic cell or voltaic cell, this is the source of electrons. And because it's a source of electrons, this will typically have a negative sign attached to it. Now, here's where things start to differentiate between real chemistry things and the rest of the world. And I know we've had this discussion before, I think. And I don't know, has anybody done the electricity part of physics yet? Some of you have. Okay, you guys know of conventional current in physics? Did you guys do electron flow, or did you do conventional current? You did electron flow. Really, that's good, because now it matches up with chemistry. You seem to know the difference of what I'm talking about. Oh, excellent. Okay, where I'm going with this is many, if not all, but almost everything, all the rules and laws governing electricity were known before people ever knew what electricity was. Does anyone remember what electricity is? Maybe, does anyone know what electricity is? It's a flow of electrons. But that flow of electrons has a bunch of rules and laws that govern it, okay? Interestingly enough, those rules and laws were determined before the discovery of the electron, okay? So this is why I mentioned this idea of conventional. Is anybody's parents an electrician, or do you guys know any electricians? Are or no? Are? Okay. He, your grandfather, I'm guessing, right? Electricians, they use what we call conventional current, okay? And again, it made sense at the time, okay? But and again, this is before the discovery of electrons. Wouldn't it make sense where energy would flow where there's an excess of energy to where there's a deficiency of energy? Kind of makes some sense, right? Until everything equilibrates. Sign-wise, if there's an excess of something, what sign might you attach to that? Plus, wouldn't you? Okay? And if there's a deficiency of something, you would probably call that negative or minus. So, electricians think of electrons flowing from, or think of energy flowing from positive to negative. Okay? But what's actually happening is where the excess of, as you just said, is electron flow, okay, there's an excess of electrons. And of course we know the electrons are negatively charged, and they're going to flow to where there's a deficiency, which will end up being the positive. You see, does that make any sense? So in science, because we know of these electrons, we typically speak in terms of electron flow theory. However, since the rest of the world, the existing world, like when people do wire and everything, they're thinking just the opposite. So this will be the test of which did you use the right-hand rule or the left-hand rule? If you know what I'm talking, if you studied electricity, you'll know what I'm talking about.
Well, we just talked about like Coulomb's law and stuff like that.
Okay, you didn't do anything about induced electromagnetic fields or anything? Okay. Did anyone else do anything with magnetism? Electromagnetism? Well, then this is a moot point. Okay. So when you go to college someday and take your first year of physics class, many of you are going to do that, I'm going to guess, right? You will use, more than likely, because most physics books use conventional current, even though they mention the idea of electron flow, though you'll use something called the right-hand rule. We, since we know about the electrons and their charge and all that kind of stuff, are going to use the left-hand rule, because all the rules stay the same. It's just everything's reversed, okay? So that theory goes something like this. It depends on whether you're talking about electromagnetism or induced magnetic fields. Let's say we have a wire that's carrying electric current, and let's say the electrons are flowing from this end to this end, okay? If you point your thumb of your left hand in the direction of the electron flow, your fingers, as they curl, show the way the electromagnetic field that would be generated, the magnetic field that would be generated from that flow of electrons. I don't know if you knew that flowing electrons induce a magnetic field. Did you? Okay. Did you use your right hand or your left hand?
Well, we didn't really do that.
Okay, that's okay. Okay, I got you. I understand. Did you guys ever, when you were like in younger classes, take like a bar magnet, throw a piece of paper over the top of it, and sprinkle iron filings on it? Yeah. Mm-hmm. You guys remember doing that? Wasn't that kind of cool? So there's magnetic field lines right there. Is what you guys were drawing, magnetic field lines, maybe? Okay. You guys may remember this discussion when we talked about spinning electrons. And this is when I introduced the left-hand rule and the right-hand rule for the reason for the arrow pointing up and the arrow pointing down. And we said that if you use your left hand, if you point your thumb up, if you curl your fingers in the direction clockwise, your thumb points up towards the north pole of an induced magnetic field. And if you had your fingers curl in the counterclockwise direction, you're kind of differentiating between the up arrows and the down arrows on the electrons. Okay, same ideas. Okay, these are all the same ideas. Anyway, so the anode is the source of electrons, has a negative sign because it is the source of electrons. There's excess electrons, has a net negative charge to start. The other piece is the cathode. I'm going to do things to these words here in a little bit. So the other side of the electrolytic cell is called, of the galvanic cell is called a cathode. Clearly, we would guess that this is where the reduction half reaction is occurring. And it will have a positive sign. You will find, I'm sure your book gives at least one or two ways of remembering which is which. You guys may end up looking stuff up on your own on the internet somewhere in which you're going to find one or two other ways. I don't really care how you remember where oxidation occurs and reduction occurs. Okay? It doesn't matter to me. But if you're looking for something, and I don't do this very often, so take advantage of it if this is something you care about. The anode is where oxidation occurs. Both anode and oxidation are vowels. Cathode is where reduction occurs. Both C and R are consonants. I don't care how you do it. There's something if you want it. And then or you can just learn Leo goes grr. Yeah, you're going to run into that. Moving on. We also need a path for the electron transfer. Now, in many cases, that's going to be a wire. Okay? Now, the little batteries that you guys use, your little AA's, AAA's, whatever you guys call those things, okay? Both of these components are within the entire case of that battery, okay? They're separated inside. Here, the little picture that we have here is they're completely separated from each other. We need some sort of way for ions to transfer back and forth between the cells to maintain a balanced charge. In the diagram that you're seeing at the bottom there, we're going to use something called a salt bridge. I'll explain more about that later. Or you can use something called a porous barrier. I don't know what happened to all our porous cups. We used to have all these little cylindrical cup things that looked actually not a whole lot different than this, except they were hollow on the inside, and they were made out of the same material as those fritted glass plates that we just used for our gravimetric analysis. Okay, so the solution could pass, and the ions, like the chloride ions, went through clearly, right? And then for some of you guys, the barium sulfate did too, but that's unfortunate. But anyway, the ions are small enough they were able to get through that. Okay, and so that would happen also. So you could actually take one of these little porous cups and put it in a beaker, and that's how you would separate your two cells instead of having two separate beakers. Also, I've done this little stupid joke before. You will see in that diagram at the bottom there, you'll see this tubular kind of structure connecting the two. Yeah, that was the original U-tube. Seriously, I mean, it's this whole. Whenever I heard the word U-tube up until 5 years ago, this is the thing that came to my mind. Okay, apparently there's something else now. I may or may not play with this later. We'll see what happens. But what you would normally do, you guys maybe possibly in biology, did you guys grow any bacteria or anything in some nutrient agar?
I did that in microbiology.
In microbiology? Okay. You guys know what I'm talking. Did you ever use Petri dishes? What was in the bottom of the Petri dish? You didn't. Agar? Agar? Okay. Nobody knows what I'm talking about.
I know what you're talking about.
Okay. So anyway, what you do is you make up this agar stuff, which is a gel-like material, okay? But you mix it in a highly, you mix it with a salt solution of some sort. The salt, it can be any kind of a salt, okay? But anyway, it's something with positive and negative ions. So instead of just using water, you'd use a salt solution of some sort. So that way, as that gel hardened, okay, inside the U-tube, you would have ions that were able to flow through that, okay? And then you would just connect the two cells So you'd have one type of solution in here, different type of solution in here. You would connect the two like that, and now we have a way for the ions to migrate back and forth between the two pieces. Okay? So I'm actually going to, the best I can, reproduce that whole drawing up here. Nothing yet. And the only reason I'm using different colors is to differentiate, to show you that there would be possibly two different types of solutions. And then, let me see, let's put the U-tube on here. Okay, and then, of course, we would have our anodes. And our cathode. And a way to connect those. All right. Is that similar?
Yes.
Okay. Up here, you can have some sort of meter. It could be an ammeter. It could be a voltmeter. Depends on what you're trying to measure. We'll talk about the difference between the two here in a little bit. Under salt bridge, is this what you were talking about? It's just used to connect, something to use to connect the half cells. But most importantly, it allows aqueous ions to flow between the cells to maintain charge equilibrium. I'll say that again, but I've already said it before. But it's a means of allowing ions to flow to maintain charge equilibrium. Now, in the bad old AP days, they actually used to make you figure out which way the electrons are going to flow, label them negative and positive, all that kind of stuff. They're starting to get away from that a little bit, but because you're going to probably run into it in your next chemistry class anyway, I'm going to keep doing it. Conventionally, although the AP would mess with this a little bit because they didn't want you to just memorize it in convention, they actually wanted you to think. Conventionally, if you're ever going to draw a cell, you would put the anode on the left and the cathode on the right. I'm going to follow that convention for now, but keep in mind you may actually have to use your brain on occasion. Okay, so if this is the anode, then what process will be occurring over here? That would be the oxidation. Okay, so this would be what we call the oxidation half cell, where the oxidation half reaction occurs. Over here, clearly, then would be the reduction half cell, where the reduction half reaction would occur. We're actually going to put things up there here a little bit. Now, the anodes, they could be a number of different things. Okay, typically they're metals. Okay, just different types of metal. I have up here, I have some zinc. It's got a little stuff on it, and some copper. Okay, we'll get to that here a little bit. Okay, they could be platinum, which is a metal, but clearly a specific type of metal. It could be graphite. Like your pencil lead, okay? Or it could be hydrogen gas. Any of those things could be utilized as a electrode. Now you might be thinking to yourself, well, how can you use a gas? Well, it would actually be in a tube. Don't draw this. I think it actually comes up later. But let's imagine that we have a tube with, say, a platinum wire in it, and then in that platinum wire, or sorry, within this, it's a sealed tube. Okay, so you have like a stopper or something here, and then you would have your hydrogen gas in here. In fact, when we get to the reduction potentials, that's actually what everything is based on. It's called a standard hydrogen electrode, and everything else is based off of that. But that's coming up here in a little bit. Let me see, what else are we going to do? This is called, clearly, the salt bridge. Okay. Another way you can do it, I've seen this done before, I don't think it works as well, is you can put just a solution in that U-tube and then take like a couple of pieces of cotton and plug it either end. That works too. I like the agar stuff. That works out pretty well. So now, remember, the anode is the source of electrons, because this is where oxidation is occurring. Electrons are being emitted from that, okay? And so they're going to go over to the cathode. So what we're doing, we've already talked about, when we're doing the redox reactions, that the oxidation, the piece that was being oxidized, was providing electrons for the piece that was being reduced. All we're doing with that battery and a galvanic cell is separating those two pieces and using a wire to connect those two pieces so that we can use that actual energy flow, electron flow, to use as energy. So we're actually physically separating those two on purpose to use the electricity for something. All right, what else do we want to do? Now, if this is the case, in general, what's going to happen to the charge of this component over here? It's going to become more positive, whereas this side's going to become more negative. Well, we're not going to, as you guys may have learned in some course at some point in time, in order to have an electric current, you have to have a constant flow of charge. Okay? It has to have a complete circuit, you guys may remember. Okay? Well, currently we don't have a complete circuit. We've got all the electrons going over here. We're having a huge charge differential. We can't have that. So that's where the salt bridge comes into play. So in order to counteract the fact that this is becoming positively charged in a net positive charge over here, we need to get some negative charges over here. Would you guys agree? Okay, so that the negative charges have a constant flow. So what's going to happen over here, whatever the anions are in the particular salt that we're talking about, they're going to flow into here, whereas clearly over here are going to flow the cations of the salt. Yes, yes. Remember, anions are negatively charged, cations are positively charged. Does anyone remember the stupid little thing? Because there are only like two stupid little things I ever teach you. If you have trouble remembering what a cation and an anion are. What's the charge on a cation? Positively charged. There's your little positive charge. For those of you that forgot. Just saying. Okay, next. I think I have everything up there. Oh, and when I wrote all this stuff up here for one of the electrodes, each electrode could be that. Okay? I'm going to actually show you some specific ones here in a little bit. Ooh, nice. Look at that. Okay. Any questions so far? All right, moving on. Do I have line notation as the next piece? All right, so obviously if you wanted to talk about a particular set of components with particular chemicals, this is kind of a real pain in the rear end to draw. Would you agree? Okay? So there's another way to do it so that people are familiar with this process where you don't have to draw all this stuff, but then also show what's involved. So this is what we call line notation, okay, which is just a shorthand way of basically talking about this without having to draw that whole thing. So it goes like this. Here would be what line notation would look like. So it would be anode. Okay. Now, what does all this mean? Well, the double line would be either the salt bridge, porous cup, whatever. Okay. The anode would be some type of metal. The cathode would clearly be more than likely a different metal or one of the other components. And then the solutions would be the appropriate solutions depending on what we're going to make. Now, I'm going to give you an example here in a second of one. So, for example, let's imagine I did this. Yeah, I did it right. Let's imagine that I use a piece of zinc metal, a strip of zinc metal, as the electrode for the cathode side or the anode side. Just for fun, I might have some zinc, let's say nitrate solution. Okay? So if I have zinc nitrate over here, does it work?
I don't know.
Oh, I thought you made a Rubik's Cube. Except all black. All black. Yes, I got it! An all one color Rubik's Cube. Yeah.
So there's like certain anodes, like you said, like the platinum metals that are
As the rest of this period goes on, we'll talk about that. Okay. Now, because this is an aqueous solution and it's a nitrate ion, what does that tell you about the solubility of this? Yeah. So it's a strong electrolyte, right? So essentially, what we have are a bunch of zinc ions floating around with the appropriate nitrate ions. You guys got that? Okay, everything's just floating around because it's complete. I'm not going to do the only reason I'm doing this is because of the stoichiometry of the zinc and nitrate. Did I have twice as many? Darn it. We'll put it over here. Boom. Okay. So all that's floating around. Let's say, just for fun, the other anode, or the cathode, the other electrode, is a piece of copper, a strip of copper. In which case, maybe the solution is copper 2 nitrate. So we've got some copper ions floating around here with the appropriate nitrate ions. Okay. Just for fun, let's say in the salt bridge we have some non-reacting species, a species that's not going to react with either the copper, the zinc, or the nitrate. Maybe some sodium chloride. Will sodium react with any of those? No? Will chloride react with any of those? Turns out no. Zinc chloride is a very strong electrolyte also. Okay? So, if this is the case, at the anode, remember oxidation occurs with the anode. What does that mean? What's going to oxidize? Can the zinc oxidize any further and become more positive? The zinc ions. Can the zinc ions oxidize any further? No. Can the zinc metal oxidize and become zinc ions? Absolutely. So what's going to happen is more zinc ions are going to be created during the oxidation process. So what's going to happen to the mass of the zinc electrode over time? It's going to decrease because it's going from zinc atoms to zinc ions. Those ions are going to dissolve in the water. So far, so good? Okay. On the other hand, and we'll talk about how we're going to be able to figure out which one's going to oxidize, which one's going to reduce here in a little bit, which is basically your question. On the other side, so now all these electrons are going over here. Okay, now there's an excess of electrons going over here. Well, there has to be a reduction. Can the copper atoms reduce and become copper negatively charged ions? Is that going to happen? No, because it's a metal, right? What can happen? Well, the copper ions that are already oxidized, okay, can accept those electrons and become copper atoms, okay, which will then plate out onto the surface of that electrode. So we're actually creating more copper atoms, neutral atoms. What's going to happen to the mass of that electrode over time? It's going to increase. But, as we said earlier, we've got a net positive charge over here now because of all these ions that are being created. We have a net negative charge over here because the positively charged ions are plating out and becoming atoms, leaving all these nitrates sitting over here. Does that make any sense? So up here in this salt bridge, what's going to happen? The chloride ions are going to travel to the left and enter this solution. The sodium ions are going to travel here and enter that solution to maintain the charge. The zinc electrode loses mass because some of the zinc atoms are converted into zinc ions, which then dissolve in the water. Because they're losing electrons. And those electrons, as we already said, are moving in this direction. And the only reason we have the voltmeter up there is I should have put ammeter for right now to actually show that electrons are flowing. Amperage is counting basically a measure of the number of electrons that are flowing. Voltage, we haven't gotten in a potential difference. Again, that's your question. Voltage is kind of like somewhat analogous to gravitational potential energy, but we'll get to that one here in a little bit. Anyway, does this kind of do you see the process here? Yes.
So the zinc metal, the neutral zinc, that just oxidizes just because it's natural?
And again, okay, and again, this is an analogy. It's not exactly the thing. It's an analogy. But will this stay suspended in air if I let go? No. It has you said the word natural, but a tendency if I were to let go because of gravity is going to fall. Well, in a very similar thing, there is a natural thermodynamic is, we're going to get into that later, reason why that's going to happen. Okay. Next. Now, the only reason I did all this, and I knew it was going to happen, is I wanted to show you how we would write this out in line notation. Here's how we would write it out in line notation. We would put zinc, timeout, we wouldn't even have to spell it. Zinc nitrate, copper nitrate, and copper. And if you want to put solid here, that's fine. Okay? So, if you see this written on a piece of paper, your brain sees this. Or not. But this is this. A little bit easier to do that, wouldn't you agree? Okay, so that's what line notation refers to. Now we're on to the question of the day. Valerie's question. It's referring to something called electric potential difference. Abbreviated EMF. For the first time, we're actually explaining what EMF is. It says electromotive force. And it's synonymous. We would use the word voltage. You're used to using the word voltage, but you guys need to be used to a variety of words that mean the same thing. Electric potential difference, electromotive force, cell potential, cell voltage. All of those are referring to exactly the same phenomenon. So electromotive force or cell potential is measured in volts, like it says there. I will explain to you or describe to you what a volt is. I'm out of room over here, so I'm going to get rid of this. AP exam hasn't done line notation for years, so you guys won't need that, but you will see drawings like this. A volt, which has the abbreviation capital V, equals or is equivalent to a joule per coulomb. So I don't know if you guys knew that before or not. Some of you may have. So a joule, as you remember, is a unit of energy. A unit of energy. Okay? And the charge on an electron is equivalent to 1.60 times 10 to the negative 19th coulombs. So one electron has a charge of 1.60 times 10 to the negative 19th coulombs. That will come in handy when we get to electrolytic cells. Now, I'm introducing the idea of equilibrium again. You guys know enough about it. You don't have to do any calculations. We've never done any calculations. But you guys know enough about equilibrium, I think, that this is going to work. We typically set cells up as far from equilibrium as possible to get the longest life out of them basically to get the longest life out of them. And basically what happens is when your battery dies, all that means is that electromotive, we've run out of one of these components. Is essentially what's happened. When your battery dies, everything's come to equilibrium. Okay? So like when we transferred energy, didn't we do a lab this year? Yeah, when we mixed two solutions together, they came to an equilibrium temperature. They were all exothermic processes, right? Well, it was like the first lab we did, wasn't it? We added a bleach with another solution. The temperature went up. We measured the highest temperature, okay, the equilibrium temperature. Everything was done. Okay. I know this is all new, okay? And right now I'm speaking a language that you guys don't know yet, and you guys need to. And I think some of you read through the book a little bit, so you had a little bit of a vague idea of what was being discussed. The next piece is now we're going to put it all together. It's called the standard cell potential, which we're going to use the abbreviation E-cell. This is going to be the first time. Usually, I've introduced what this means before we get here, because we usually do thermodynamics before. But all that means is standard. Anytime you see that superscript 0, it means standard. If you really want to know what that means, we're referring to, right there, I'm going to describe it to you. The standard state, if it's a solution, it's always 1 molar solutions. So if there is a substance that we're referring to, and we're saying it's in a standard state, and it's a solution, that means it's a 1 molar solution. If it's a gas, it means it's 1 atmosphere of pressure. And under all states of matter, it's at 25 degrees Celsius. So the standard set of conditions are 1 molar solutions, 1 atmosphere of pressure for gases, and 25 degrees Celsius for all of those things. Those are the standard conditions. If it's anything other than those, then the values that are going to be listed in the table that we're going to refer to here in a little bit, they're going to be slightly different. Okay, so you're almost always, for especially this course and your next course that you guys take down the road, almost everything's going to be in standard conditions with that little circle right there. Yes? Synonymous with cell potential, cell voltage. I just gave a bunch of other phrases. Cell potential, cell voltage. You can put those under there too. Those are all the different words or phrases that mean the same thing. Electromotive force, cell potential. Look, up in F, it says electric potential difference. That's one phrase. Electromotive force, second. So cell potential difference, electric potential difference or electromotive force are measured in volts. But you can also use phrases cell potential, cell voltage. All those phrases refer to the same thing. Yeah. Voltage means all those things. Yeah. All the reason I'm saying those to you, because you're going to run across all of those phrases. I don't want you going, what does that mean? I understand. I get it. All right, moving on. We're going to use, as it says there, the standard reduction potentials, which I believe it says table 20.1. Yeah, that's not going to happen because we have a new book now. So it's table 19.1. It's on page 901. So if you guys could all flip to that, because this is important. This is a small list. Well, there's only how many? Oh, well, that's not a bad list. It's not bad. There's also in the appendix, I think it's 18 and 19. Forget it. I might not be right. Hang on to that page there, just in case. 13 and 14. I was close. Okay, so on pages A13 and A14, there's some more that aren't already listed there. Now, let's looking at that table that you're currently looking at. I don't know where my book is. Anybody know where my book is? I found it. A couple of things I want to point out on that book. What page is that on, 901? Okay. First of all, you'll notice that it's organized in decreasing potential. Decreasing electric potential. From top to bottom, decreasing electric potential. You guys agree? Now, look at the top reaction there. What is that showing? But what's happening to the fluorine? It's reducing. Notice that it is at the high, it's at the very high end, which means it is very easily reduced. Now, I know I'm going to have you pull some information from your previous chemistry class, your first year course on this. Does it make sense that fluorine would be the most easily reduced? Now, what does it mean to reduce? Gain electrons. Why is fluorine, so in other ways, in some ways this is saying that fluorine wants electrons. Why is that? It's no, electronegativity has nothing to do with it. Thank you for saying that, because so many of my students confuse the issue there. They only, but what else? There's one other thing. Actually, the biggest thing. Okay, well, doesn't chlorine want them? And bromine? Thank you. It's the smallest and the highest nuclear charge. Okay, so does oxygen want electrons? Right. But it's not so much that it's closest to 7, it's the fact that its nuclear charge is, its ratio is higher in fluorine than it is oxygen. Its nuclear charge. The number of protons. Right? It's because oxygen, nitrogen, oxygen, and fluorine are all going to form negative ions because they're all going to gain electrons. Fluorine has a greater potential of gaining electrons because it's got a greater nuclear charge. It's smaller because it has a greater nuclear charge. High propensity for gaining electrons. What's that? Yeah, they're just the same number of energy levels. Yes. Okay. So that's why that's up there. Anyway, I just wanted to point that out to you. Now, remember earlier I had said that all of the voltages or the electromotive forces, the electric potentials, are based on the hydrogen gas. Okay, looking almost nearly in the middle of that list, what do you see? Hydrogen gas. Right? Okay. That was assigned a 0. Nobody measured that. It was assigned a 0. And then experiments were done by using the hydrogen to many of the other ones to find out what their potential differences were. Okay? So everything, all those electric potential differences are based on that's called the standard hydrogen electrode, or SHE, otherwise known as SHE. So you may hear us refer to a SHE once in a while. That's not talking about one of you young ladies. It's talking about the standard hydrogen electrode. Now, the other thing you're going to notice about that table, first of all, if you read the name, reduction half reaction. This is called the standard reduction potential table. Everything is written as a reduction. As you guys all know from our redox balancing, you can't have a reduction without an oxidation. So what we have to do is figure out which of these species is going to oxidize, which one's going to reduce. The one that we decide is going to oxidize, we have to take that reaction that's provided and reverse it to make it into an oxidation. You guys following? I'll tell you how to know to do that here in a little bit, or which one we're going to end up needing to be reversed. But I'm just saying, these are all written as reduction potentials. Okay? If you need one to be an oxidation, you reverse the reaction. All it does is changes the sign. Okay? Because you'll notice that in the top half they're all positive, and the bottom half they're all negative. Okay. We're getting there. We're almost there. All right, so the third asterisk, I just told you, is based on the standard hydrogen potential, and it's assigned a value of 0.00. Here is the biggest thing right here. E cell is positive for a spontaneous reaction. Now, the phrase spontaneous reaction is no longer in favor in the AP community. They substitute that now with the phrase thermodynamically favorable. Get used to both. So a spontaneous reaction, meaning one is going to progress on its own without any outside influence. Another phrase for that the AP is favoring now is thermodynamically favorable. Since we haven't really learned much thermodynamics yet, we'll probably lean towards spontaneous for right now. Okay, so that means any combination of these things has to result, when we add them up, into a positive E cell. So let's use the ones that I already have written up here just for fun. And that's what example number 1 is anyway. So we're going to determine the E cell, the standard cell potential, for a galvanic cell constructed with copper, zinc, and the appropriate copper and zinc solutions. 1 molar copper and zinc nitrate solutions. Exactly as I've written up here. That's why I did this, by the way. Okay? First thing you're going to do is write the more positive E reduction potential first. So we look at our handy-dandy little chart and find the more positive one. Well, we see copper. Right above the standard hydrogen potential, we see the copper. No, we don't. My bad. Well, it's a little bit above it. Okay, copper with plus 2 electrons, right? I'm going to erase all this stuff. Copper, what do I have? Blue up here? So we have the copper ion plus 2 electrons forming copper. Whoops, I didn't give myself enough room. My bad. Okay, and its reduction potential is, I think, 0.34 volts. Is that correct? Yeah. 0.34 volts, okay? Then we find the other process. In this case, it's zinc. We find its reduction potential. You'll notice that it's a little bit about halfway down below the hydrogen potential. Do you guys see it? Except, remember, that's written as a reduction. We need that to show a oxidation. So we have to reverse that reaction. So we're going to go zinc yielding zinc ion plus 2 electrons. Would you guys agree? So we reverse the reaction. That means we're also going to have to reverse the sign of the reduction potential and make it an oxidation. And let me see, I don't have that memorized. It's negative 0.76. So we make it a positive 0.76. Then we just add the two together. So essentially what we have here are the two half reactions. We have a transfer of 2 electrons. The copper reduced, the zinc oxidized. We add the two reactions up. we get copper ion plus zinc yielding copper metal and zinc ions. And its reduction, or sorry about that, the cell potential, which we call E cell, is just the sum of those two. So we're looking at 1.10, right? I'd get in the habit of including the signs, that way there's no ambiguity. So, possibly now I can answer Valerie's question, which do you remember your question?
Are there certain cathodes, like there were like certain scale?
Okay.
Listed them in red.
Say this again.
Like so you listed them over there.
Oh, well, as far as what metals are, it could be anything.
Okay.
And here's where I'm going with this. Depends on what it's with.
Okay.
And that's, okay, so now how are we going to know which one's which? Which one's anodes, which one's cathodes? Here's, in my opinion, the best way to do this. The one that is most negative is the one that's going to be the anode. Think that through. Because when you add the two together, in order for it to be spontaneous or thermodynamically favored, the sum has to be positive. Is that right? So let's say we pick, just for fun, gold 3, which is about a fourth of the way down on the above the. Anyway, it's about the sixth one down or so. You guys see gold 3? Mm-hmm. What if I were making this? We're not in Olentangy, so this would never happen. So we'd never have a gold electrode. Thank you. That was good. Okay, but let's say we're going to make a cell between gold and silver. Once again, we're not in Olentangy, so we wouldn't do that. Okay? Which one is going to be... Now notice that they're both positive, right? But we have to reverse one of them. Which one are we going to reverse? Well, it would be the silver to make that the oxidation, which even though that's now going to become negative, the other one's still more, you know what I'm saying? Or, if we go this way, even if we use one of the ones that's already in negative reduction potential, like zinc, okay? By reversing it, it's going to make it positive. But if we reverse the one that's more negative, the other one's still going to be more positive enough. Possibly. It's still going to give us a positive overall. Now, what if we picked calcium? No, let's go with aluminum because we can actually pick pieces of aluminum. Let's pick aluminum and zinc to make a cell out of. Which one are we going to reverse? The more negative one, which is the aluminum. Since it's more negative than the zinc, when we reverse that, it's now going to be more positive than the zinc. You guys following there? So that's basically what we're doing. Find the more reverse the more negative one and make that an oxidation. In that case, the aluminum would be the anode. That is right. Because it's for the oxidation. It's going to oxidize. When it's combined, when aluminum and zinc, when aluminum and zinc are together, zinc has a greater reduction potential. Aluminum has a greater oxidation potential. So that's why you said, are there certain ones that are anodes, certain ones that are cathodes? Now you can see we've had zinc as both a cathode and an anode now. It depends on what it's with. And the bigger the difference, and this is where, remember I used the analogy earlier about gravitational potential energy? Okay, so in which case would this have more gravitational potential energy? When it was here or here? You even cringed a little bit, I'll bet anything, didn't you? Okay, at first you just cringed a little bit, but then you cringed a lot. Okay? Same kind of idea. The bigger the difference between the two, that's what it means by electromotive force. It's the force of electrons that are being, I guess I don't know whether you want to look at it as a push or a pull, it doesn't really matter. If you're looking at the copper side, it's pulling the electrons from the zinc, or in other words, the zinc's pushing the electrons to the copper. Does that help any? And the bigger that potential difference, the greater that pull or push is going to be. Just saying. Okay. Oh, I do have to say this. Under the key points, the second bullet point is incredibly important because there's going to be something similar in our next unit that we do that is not going to be intensive. Does anyone remember what intensive properties are? They do not depend on the quantity. Okay? These are intensive properties. It doesn't matter how much copper you have. It doesn't matter how much zinc you have. Reduction potentials are intensive properties. So as long as we're at those, remember there's standard reduction potentials. As long as we're at 1 molar solutions, 25 degrees Celsius, these are the reduction potentials. Okay? Doesn't matter if you have a liter of it, 5 milliliters of it, it's still going to have the same reduction potential. In thermodynamics, we're going to find out those are extensive properties in which it does matter how much. And so we have to make sure that we're differentiating between the two. All right. And as I said, that last bullet point down there is the magnitude of E cell indicates the driving force of the reaction, the bigger push and pull. I don't know how much time we have left because we have a weird schedule today.
We have 3 minutes.
Do we really?
This class is at 22, it's 19.
This class ends at 22. It's 19. That's 3 minutes. All right. Well, I think that's a good place to stop. Darn it. Okay, so it's going to take 2 more periods.